Today we are going to discuss reactions of haloarenes. First is nucleophilic substitution. Aryl halides are extremely less reactive towards nucleophilic substitution reactions due to following reasons. First reason is the resonance effect. In haloarenes, the electron pair on halogen atom are in conjugation with pi electrons of ring, and the following resonating structures are possible. So let's draw the resonating structure of haloarenes. So let's draw the structure of chlorobenzene. So this is the benzene ring in which alternate single and double bonds are there, and here it is bonded to chlorine. And we know chlorine has three set of lone pairs. And these lone pairs are in conjugation with the benzene ring. That's why these lone pairs participate in the resonance of benzene ring. So chlorine shift one of the lone pair between carbon and chlorine bond, and the pi bond move to the next carbon. So here you will get the next resonating structure. So these two bonds remain as it is. Carbon-chlorine bond become double, and chlorine will develop positive charge as it is donated lone pair to the benzene ring. And at this position, negative charge will be developed as pi bond move to this carbon. Now in the next resonating structure, this negative charge move between these two bonds and the pi bond move to the next carbon. So here you will get the next resonating structure. Here these two bonds remain as it is. Chlorine already has the positive charge. As this negative charge move between these two bonds, new bond will be formed at this position, and as the pi bond move to the para position, negative charge will develop at para position. Now this negative charge move between these two bonds and pi bond move to the next carbon. So here you will get the next resonating structure. In this resonating structure, these two bonds remain as it is. Chlorine already has the positive charge. As the negative charge move between these two bonds, new bond will be formed at this position. And as the pi bond move to this position, negative charge will be developed at ortho position. So that's how you will get these four resonating structures. When you observe these resonating structures, you will see carbon-chlorine bond is double bond in three resonating structures. Now let's read from the book. Carbon-chlorine bond acquires partial double bond character due to resonance. As a result, bond cleavage in haloarene is difficult than haloalkane. Therefore, they are less reactive towards nucleophilic substitution reaction. Now come to the next point. Difference in hybridization of carbon atom in carbon-halogen bond. In haloalkane, carbon atom attached to halogen is sp3 hybridized, while in case of haloarene, carbon atom attached to halogen is sp2 hybridized. So here when you see the carbon in haloarene, this carbon has made 3 sigma bonds. That's why the hybridization will be sp2. While in case of haloalkane, this carbon has made 4 sigma bonds. That's why the hybridization is sp. The sp2 hybridized carbon atom has greater S character, is more electronegative, and can hold electron pair of carbon-halogen bond more tightly than sp3 hybridized carbon in haloalkane with less S character. So when you compare sp2 hybridized carbon with sp3 hybridized carbon, in sp2 hybridized carbon, when you check the percentage of S character, here there are 33% of S character, while in case of sp3 hybridized carbon, there is only 25% of S character. As there is higher S character, it is more electronegative. That's why sp2 hybridized carbon can hold the electron pairs more strongly. That's why the bond length is shorter. That's why the bond length is shorter than the bond length of sp3 hybridized carbon and halogen. And the shorter bonds are difficult to break. That's why it is written here, sp2 hybridized carbon has greater S character and it is more electronegative, can hold electron pairs of carbon-halogen bonds more tightly than sp3 hybridized carbon in haloalkane with less S character. Thus, carbon-halogen bond length in haloalkane is 177 picometer, while in haloarene it is 169 picometer. It is shorter than the haloalkane. Since it is difficult to break a shorter bond than the longer bond, therefore haloarenes are less reactive than haloalkanes towards nucleophilic substitution reactions. Now come to the third point. Instability of phenyl cation. In case of haloarenes, phenyl cation formed as a result of self ionization will not be stabilized by resonance. Therefore, SN1 mechanism is ruled out. Now let's try to understand it. For SN1 reaction mechanism, you need to break the bond between carbon and halogen. And when the carbon-halogen bond is broken, halogen leaves the molecule in the form of halide ion. So when it leaves the molecule in the form of halide ion, you will get phenyl cation. So here, positive charge will be developed at the benzene ring and Cl will leave the molecule in the form of chloride ion. So this is the phenyl cation. As in case of phenyl cation is at the sp2 hybridized carbon, which is more electronegative. That's why phenyl cation is less stable. And as the formed cation is less stable, it cannot undergo SN1 reaction mechanism. So here, that's how we can rule out the possibility of SN1 reaction mechanism in case of haloarenes. Now come to the fourth point. Because of the possible repulsion, it is less likely for the electron-rich nucleophile to approach electron-rich arenes. In case of SN2 reaction mechanism, nucleophile directly approach to the carbon. But as there is pi electron cloud in case of haloarene, there is a pi electron cloud. This pi electron cloud repel the coming nucleophile. And because of this repulsion, nucleophile cannot directly approach to the haloarenes. So that's how we can rule out the possibility of SN2 reaction mechanism as well. Now let's read from the book. Replacement by hydroxyl group. Chlorobenzene can be converted into phenol by heating aqueous sodium hydroxide solution at temperature 623 Kelvin and pressure 300 atmosphere. So here when you see chloride group is replaced by the hydroxide group, means this is a kind of nucleophilic substitution reaction. But as we have ruled out the possibility of SN1 reaction mechanism, haloarene may undergo SN2 reaction mechanism at a certain conditions. So at the extreme condition of 623 Kelvin temperature and 300 atmospheric pressure, it may undergo SN2 reaction mechanism. Chlorobenzene, when reacted with NaOH at 623 Kelvin temperature and 300 atmospheric pressure, it gives phenol. The presence of an electron withdrawing group like NO2 at ortho and para positions increases the reactivity of haloarenes for SN2 reaction mechanism. When you see presence of nitro group at para position lowers the temperature for the reaction. Now it can react at 443 Kelvin temperature with NaOH and gives you para-nitrophenol. But when nitro group is present at ortho as well as at para position, it can react at 368 Kelvin temperature even lower than before. And in the third example, when you see both ortho and para positions are occupied by nitro group, it can undergo reaction just on warming up the reaction mixture. The effect is pronounced when NO2 group is introduced at ortho and para positions. However, no effect on reactivity of haloarene observed by the presence of electron withdrawing group present at meta position. The mechanism of reaction is as depicted. Now let's try to understand why there is no change on the presence of electron withdrawing group at meta position, and it enhances the reactivity when the nitro group is present at ortho and para position. So let's try to understand this reaction mechanism by drawing it ourselves. First of all, draw the structure of chlorobenzene. So this is the chlorobenzene. This is benzene ring and here chlorine is bonded. When nitro group is present at para position. So here I am going to draw nitro group at para position. So when it reacts with nucleophile OH negative ion, it will make bond with the carbon, and to make the bond with the coming nucleophile, this pi bond move to the next position. So as a result of it, you will get, this is benzene ring. Here nitro group is bonded. These two bonds remain as it is. Now here chlorine is already bonded to the carbon, and now new bond is formed with the OH group. As the pi bond move to the next carbon, negative charge will develop at ortho position. When this negative charge again move between these two bonds, this pi bond move to the next position. So here you will get the next resonating structure. In this resonating structure, this bond will remain as it is, and here OH group and Cl group is bonded, and here NO2 group is bonded. As the negative charge move between these two bonds, new bond will be formed at this position, and negative charge is developed at para position. Now here you can see at para position nitro group is already bonded. So it can withdraw electron density from this negative charge, help to stabilize this resonating structure. Now in the next resonating structure, negative charge will move between these two carbons, and pi bond will move to the next carbon. So here you will get the next resonating structure. In this resonating structure, this bond will remain as it is. Here Cl and OH are bonded to the same carbon, and here NO2 group is bonded. New bond will be formed at this position, and negative charge will be developed at ortho position. So here in these resonating structure, you will be able to see clearly that when negative charge developed at para position, nitro group present at para position stabilizes that resonating structure. So that's how the transition state has been stabilized by the nitro group present at para position. Now in the next step, when this negative charge moves between these two carbons, it expels the chlorine in the form of Cl negative ion, and here you will get the product. So in the product, bond will be formed at this position, and rest of the bonds will remain as it is. Here nitro group was bonded, and here you will get the OH group. So this is the product of the reaction. This step was the slowest step, and this one was the fastest step. Now let's see when electron withdrawing group is present at ortho position. So here when you see in this resonating structure, when nitro group is present at ortho position. So let's draw the structure when the nitro group is present at ortho position. Again, I am drawing the benzene ring. Here chlorine is bonded, and here nitro group is bonded. When it reacts with OH negative ion, this OH negative ion will get attached to the carbon to which chlorine was bonded. And to make bond with the coming nucleophile, this pi bond moves to the next carbon. So here you will get the transition state. In this transition state, these two bonds remain as it is, and here nitro group was bonded, and now OH will get attached to this carbon to which chlorine was bonded. As the pi bond moves to this position, negative charge will develop at this position. In this transition state, when you see nitro group is present where negative charge has developed, so it can withdraw electron density from the negative charge, and it can stabilize this resonating structure or this transition state. Now in the next resonating structure, this negative charge will move between these two carbons, and the pi bond move to the next position. So here you will get the next resonating structure. Here this bond and these bonds will remain as it is. Here NO2 group is bonded. Now new bond will be formed at this position, and negative charge will develop at this position. Now in the next resonating structure, this negative charge will move between these two carbons and pi bond move to the next position. So here you will get another resonating structure. In this resonating structure, this bond will remain as it is, which is bonded to NO2 and OH. Here is Cl. Now new bond will be formed at this position and negative charge will develop at this position. Now this negative charge move between these two bonds and expel the Cl in the form of Cl negative ion. So here you will get the product of the reaction. In this product, these two bonds remain as it is. Here NO2 group is bonded and now here you will get OH and new bond is formed at this position. So that's how you will get your product. So when you see in one of the resonating structure, NO2 group help to stabilize this negative charge by withdrawing electron density from ortho position. So that's how transition state is stabilized by the presence of nitro group at ortho position. So these are the transition states and 3 resonating structures you will get in the transition state. In the previous example also, these are the transition states which has 3 resonating structures. Now let's draw the structure in which nitro group is present at meta position. So here this is the benzene ring. Now nitro group is bonded to meta position and here there is chlorine. When it reacts with OH negative ion, OH negative ion will get attached to the same carbon to which chlorine is bonded, and to make bond with the OH negative ion, this pi bond move to the next carbon. You will get the transition state in which OH is bonded to the same carbon to which chlorine is bonded and negative charge will develop at the ortho position and here there is NO2 group and these two bonds remain as it is. Now this negative charge will move between these two bonds and pi bond move to the next position. So here you will get next resonating structure. For this transition state, here these two bonds remain as it is and here NO2 was bonded. Now new bond will be formed at this position and negative charge will develop at para position. Now this negative charge move between these two carbons and pi bond move to the next carbon. So here you will get next resonating structure. In this resonating structure, here NO2 group is bonded, here Cl and OH are bonded. This bond will remain as it is, new bond will be formed at this position and negative charge will develop at this position. Now this negative charge move between these two carbon and expel the Cl in the form of Cl negative ion. So here you will get your product. In the product, these two bonds remain as it is. Here nitro group is there. New bond will be formed at this position and in the product you will get OH. But when you see the resonating structure of transition state, so when you observe these resonating structure of transition state, negative charge is developed either at ortho positions or at para position. But nitro group was not there to stabilize that negative charge. So that's why the presence of nitro group at meta position doesn't increase the reactivity of haloarenes. Now let's read from the book. Can you think why does nitro group show its effect only at ortho and para positions, not at meta position? As shown, the presence of nitro group at ortho and para positions withdraws the electron density from the benzene ring, thus facilitate the attack of nucleophile on haloarenes. The carb anion thus formed is stabilized through resonance. The negative charge appeared at ortho and para position with respect to halogen substituent is stabilized by nitro group, while in case of meta-nitrobenzene, none of the resonating structure bear negative charge on carbon atom bearing the nitro group. Therefore, the presence of nitro group at meta position does not stabilize the negative charge, and no effect on the reactivity is observed by the presence of nitro group at meta position. In the next video, we will discuss electrophilic substitution reactions.